our examples of multiple regression so far, we've used the following model to predict y. So y would be a constant, which is the intercept. Plus a multiple of the first independent, plus a multiple of the second independent, plus a multiple of the last independent. So that's a multiple linear regression. Okay, it's multiple because there's more than one independent variable. It's regression because you predict y from the x's, and it's linear because we don't have x's squared or multiplying independent variables. And so, for example, what this means is x1 increases by 1, holding the other variables constant. Predicted y goes up by b1. Okay, and that's true no matter what the value of x1 is. But often in situations, we have nonlinearities in interactions. So what does that mean, and how do we test for those? So a nonlinear effect x1 would have a nonlinear effect on y if basically you don't have this constant slope. In other words, if x1, it may be if x1 increases by 1 when x1 is small, the effect would be b1, and if x1 is big, the effect might be something different. Okay. To model possible nonlinear effect of an independent variable, there's a couple ways to do this, but a common approach is insert like x1 squared, x2 squared, etc. as independent variables. And if the square of an independent variable has a low p-value, let's say less than 0.1, then the independent variable has a nonlinear effect on y. Now, what does an interaction mean? Suppose we're trying to predict sales of a product, x1 is price, and x2 is advertising. Okay, so we would say price and ads interact to predict sales if the effect of, let's say, changing the price, changing the advertising depends on the price. So you can see up here, no matter what happens, no matter what the value of x1, if it goes up by 1, predicted value of y goes up by b1. It doesn't matter what the other independent variables are. But in real life, probably price and advertising do interact. I would think if you increase the advertising at a really high price, it doesn't help. But at a low price, it probably helps more. So how do you test for interaction? So the test of x1 and x2 interact, and this happens a lot in the sciences to try and determine the effect of, let's say, pressure and temperature on yield of a process. Pressure and temperature may interact. The test of x1 and interact in predicting y include their product as an independent variable. And if that has a low p-value, then x and y interact. Sorry, x1 and x2 interact. In predicting y. Okay, so let's take a concrete example. If you live in a cold weather area, you're familiar with the wind chill index. It basically drives your life during the winter. They say the wind chill is like -20 or -30. You don't want to go outside. If you live in Florida or Hawaii or Mexico or India, you probably don't care. Okay, So what I have here is a bunch of wind speeds in miles per hour and temperatures and what the wind chill index is. So for example, if we had a temperature of minus 40 and a wind of 5 miles an hour, that would be a minus 57 wind chill. Okay, so this is what you're trying to predict. And this would be x1 and x2. Okay, so to test for nonlinear interactions in predicting the wind chill index from wind and temperature, what would we do? We would square each independent variable. So there's temperature squared. There's wind squared. And we'd include the product of them and at column n times column O as an independent variable. Okay, first we're going to run the linear model just straight off. So if I predicted column J from n and O in the linear model worksheet, here's the results. And it's a really good R squared. We have an R squared of 0.993. We've got a standard error of 2.79. Okay, but that standard error is the key, as we know, to interpret, let's go 994 here. Adjusted R squared is adjusted for the number of independent variables. Okay, we have not rigorously defined that. Okay, but you can see we have really low p-values. Wind and temperature definitely do affect the wind chill index in an obvious fashion. Higher wind, lower wind chill. Higher temperature, basically, the lower the temperature, the more negative the wind chill. Okay, I should say higher wind, yeah, lower wind chill, which is worse, and higher temperature, a higher wind chill, which is sort of better. Or lower temperature, the wind chill drops, as we'd expect. But keep an eye on that standard error of 2.79. Okay, so now the next step would be to run a regression with all of these as the independent variables. Okay. So we predict y from these 5, and here's the results. We get pretty much the same R squared, but the standard error is cut by 2/3 to about 0.89. Remember, it was what? It was 2.79. Okay. Now, what variables are significant? Look at the p-value column. Everything's significant except the temperature squared. So we would delete the temperature squared because it has a high p-value, and we get here the final regression. The standard error drops to 0.89. And remember, that's 1/3 of our original standard error. And then here would be all the p-values are really low, incredibly low. And so if you wanted to have a simple formula for the wind chill index, it would look something like this. So it'd be minus 8.01 plus 0.00649 times the wind squared plus, this is the interaction term, 0.034 and a 7. See, that's got wind times temperature. So in other words, the effect of the wind will depend on the temperature and vice versa because of that term. Minus 0.79372 times wind plus 1.20361 times temperature. Okay, and there, when you could plug in a particular value of wind and temperature and get a predicted value for the wind chill index, and 95% of your forecast should be off within 2 times 0.89 or 1.78. So that's an example of how to do nonlinearities in interactions. Again, the main idea was square each independent variable. If the square is significant, you have a nonlinear effect of that variable on y. If not, drop the squares and multiply each pair of independent variables to test for interactions. Drop the pairs that are insignificant. If they're all dropped, there's no interaction. And in this case, like wind and temperature was significant, so we left it in. So there was an interaction between wind and temperature to affect wind chill.
Okay, so thanks for watching, and there's a free course, a free 21-day course from Dr. Winston, and all of these videos are coming from one of 3 books. So first, this one, which you can see here at the top of the screen, Microsoft's book, which has 355 reviews, and then it's, let's see, 4.6 stars. It's coming from this book as well, his marketing analytics book, which is down here, and you can sort of see 4.5, or his newest book, his analytic stories book, which is here. And with that one, you can see it's 4 point something, or maybe even 5. I don't think it's 5. Yeah, 4.8. And so, yeah, anyways, in the description, there's a free 21-day course from Dr. Winston, or you can go to excelwithwayne.com/free, and it'll be there. But again, thanks for watching, and if you have any questions, just please let us know. Thanks.